Rahul. Easier than expected. Okay. Okay, and others. Parmita, Rahul.
Yes, I thought it was a little bit easy.
Easy. Okay.
No, I expected it to be very hard. I did not do very much preparation.
Okay. Okay. And Rahul and Parmita, what's your thought on the quiz 2? Difficulty level and easy. Okay, Parmita. Okay. Okay. So if you have any doubt in week 10 and week 11, so you can ask. Any query in any topic in week 10 and week 11, so you can tell me and we can discuss. No query. So,
yes, the Rabin-Karp, that one algorithm, it was difficult to understand.
Rabin-Karp. Okay. Sure. Okay.
And sir, there is Trie something.
Yeah, try topic. Okay, okay.
Yeah.
Okay, sir. Okay, I'm sharing my screen. Just my screen is visible.
Yes, sir.
Okay, so for Rabin-Karp matching, basically we want to skip some matching process. So how we can skip the matching process to reduce the complexity or reduce the work for the pattern matching. So what we will do according to the Rabin-Karp algorithm. So suppose here Rabin-Karp is basically work according to the integer matching type of the concept. So simply we can match the integer value. Two integer value we can easily match by the equal sign. So this concept we are actually using in the pattern and text matching. So how we will how will we do this process? So basically, what we will do. So for example, if we are using the base 10 numbers, okay. So our text is equal to like this: 6 2 1 8 3 9 4 5 7 6 2 8 3 7. Okay, and our pattern is for example 6 2. Okay, so how we can match this pattern in our text T? So we can apply the simple integer matching process. We can take directly this 62 value. So for example, this 62, and we can directly match this 62 by 2 digit of text every time. So we will scan our text. We will scan our text and we will take the 2 characters in our text and we will compare directly by after converting this value in a integer format. So for example, initially if this value is in the strings format, but all characters contains the digits value, or we can say the numeric value. So we can directly match like this. So we will directly check this 62 by this 62, and we will compare it. So this value, if this value is matched, we will return the index of the match, and otherwise we will scan one position right. Okay. So for example, for the second match, we will compare this 2-1 by this 62. Okay, so same thing. So we'll repeat. So 2-1 is not equal to 62. Same process. We will repeat 1-8 to 62. This is not equal. Then we will repeat the same 8-3 by 62. So by this way we will match every two characters in our text by our patterns. But what will be happen when if our pattern is a long? Okay, so if our pattern is a long, so definitely if this compare values also take the times, or what we will do if our pattern and text is is in the text format, text character. So how we can apply this Rabin-Karp algorithm on our text based strings? So we can simply first convert our text into a digit forms. So we can apply any algorithms to perform this task. We can relate every character by any number by a digits. So for example, in English alphabet we use the 26 characters. So we can assign a mapping for each character. So we can assign a unique mapping for each characters, and we can convert these characters into a digits form. But still, after we want to match. So this small value here, this 62 is a two digit. But what happened when our pattern is a long? So this value is this value will also become a long. So in that case, the efficiency will reduce. So in that case, in the Rabin-Karp, basically we select some q value. So q value is basically we select for the prime value. So we can select any large q value, or this is a prime number. So for example, in this example, if we are selecting this q is a 13. Okay, so this 13, and we will retrieve a reminder value for our pattern. So reminder value for pattern, we can simply calculate using this formula 62 divided by 13, and what is the reminder is. So this 13, so 52, this is 10. Okay, so reminder is 10. So we can apply this formula, reminder are equal to q mod. So this p mod q. Using this formula, we can get this reminder value for pattern. After getting this pattern for the after getting this reminder for the pattern, one sec. Okay. So we will so after getting this reminder value 10, we will apply this p mod q process on our text. So we will scan our text, and we will just check that what is our reminder. Okay, so instead of compare complete pattern value by the text, we will compare the reminder value for each text with the size of p. So here the size of p is 2. We will apply this reminder comparison on each two characters of the text. So for example, this 62, we will calculate the reminder for this. So this basically we will apply this mod q. So what will be the reminder for this 62 is a same 10. So we will get this value 10 when we are getting the 10 value. Okay, so when we are getting this 10 value, so that means our characters, our substring can be a pattern, but we cannot show this is a pattern. So after getting the equal reminder value, we will perform the string matching also. Okay, we will perform this string matching concept. So so for example, here we are getting this 10 reminder, which is same as a pattern reminder. So we consider this could be a similar, but for verify, we have to check one by one. So this 62 is a 62. This both are equal. We have to check this is a in the extra part. So we can simply check this 62. So after getting the same reminder, we will check the similarity of this. We are doing this because we can get the same reminder for different value. So because of that, this is the extra part, but we will perform this string matching only for the text part, which we are getting the same reminder. Okay, so for 62 we will perform. After that, for example 21. So for 21, we will get the what will be the reminder. So this is 13, 8. This is a 7 plus 8. Okay, so this is a 8. So we will not compare for this. Here the reminder is different. Here the reminder should be 10, but here the reminder is 8. So we will not compare this string because the reminder is different. So same process we will repeat for every pair of 2 digits. So for the 18, so we will get the 5. So we will not perform the matching for this part. Same for the 83. If 83 is, so what will be the 18, 78, and this is the 5. We will not perform the task. We will not perform the string matching for this. And now, so 83, now 39. So 26, and after that, 4 and 9, 39, 0. Sorry. So 39 is 0. We will not perform the task. Same for the 94. So we will repeat this process for every 2 characters in our text where we are getting the same reminder. We will check. If the value is equal or not. Okay, that part we will perform because maybe some value will return the same reminder, but both are not equal. So that is called the false. That is called the some term is used. So if you can see in the last part, false positive. Yeah, so you can see this example. So in this example, so here the pattern is this. So pattern is a long value, and the text is also a long value. So instead matching of this big value in our text, so we can simply take a q value for the mod formula, and we can get this reminder value for the pattern first. So we are getting 7 here. After that, we will take 5 characters from the text t, and we will calculate the reminder for each combination of 5 characters in our text. If we are getting the same reminder, then we will perform the we will check the we will validate our similarity. Okay, we will validate our similarity for the pattern and in our text, because here you can see our pattern, our reminder for the pattern is 7. Here you are getting for reminder for this value 31415 mod 13 equal to 7. Okay, here also you are getting the 7 reminder for this value 67399, but our pattern is 31415. So this is not equal to basically, but the reminder are same. So because of that, we have to perform some extra scanning to match this value to check if the value is similar or not. If reminder is same, we will perform this validation after that. So we will perform this validation only for that part which are returning the same reminder. Okay, so here we are actually saving some matching part for that substring. Those are not returning the same reminder. So for example, this is returning 8, this is returning 9. So we will not compare this part to our pattern. So we can skip this part to our for comparing to our pattern if we are not getting the same reminder. So this is basically a concept of the Rabin-Karp algorithm for the pattern string matches. So any question in this topic?
Sir, what happens when there are more than 10 characters? Here we can say 0 to 9. Okay. But if there are more than 10 characters,
So we can assign, we can use any mapping techniques. So for example, if our character have, so in English character, so for example, we have 26 characters in English. So we can assign any digit combination. So for example, A, we can assign 2-digit number like 1, 3, and we can assign B like any 2-digit value we can assign for all 26. If it is hard, so that is possible. So like this is 14 for C, like this is 15, like this. Okay, so we can map this character to digital digit process. So here you can see for sigma is equal to a1 dot to a k, treat each letter as a digit in base k. So actually we will perform this mapping process first. We will convert our text string into a digit strings of the base 10. After that, we will perform this Rabin-Karp algorithm.
Sir, once we check,
Your voice is not clear. Who is this?
once we have got a match for the modulo for the hash value, then we have to check the individual ones also, right?
Yes, yes. Then we will have to validate our pattern is similar to this match or not. If we are getting the same reminder, then we will validate also after the matching with the pattern and the that part, sub part of the text. Otherwise, if we are not getting the similar reminder, we will not perform this task.
So the selection of this, the number, the selection of this hash value, the hash function. So using 13 or anything, that is our choice, right? In
Yes,
general.
yes. We can take any prime number. Okay, so we can take any prime number, or we generally we take the large value for this. So instead do all computation and comparison modulo is suitable prime q. Yeah, so we can select any prime number for the division, and after that we will match only the remainder value. Any other query in this? Okay. Next topic is trie. Someone is asking the trie. So trie is also a different type of data structure. It is similar to a tree, but actually we use this data structure for different purpose. So basically for information retrieval. Okay, so this is a special kind of tree, and basically we use for this is a information retrieval, and this retrieval inside this TRIE part of the retrieval, the name is we assume that this name is assigned by this retrieval part, it trie, and this is a tree structure. And when we use this tree, for example, if we are storing some words, okay, where these words can be contain a common prefix. Okay, so in that case we can store these type of words. So for example, dictionary, if we want to store the dictionary words in our data structure, so we can use this trie, and we can retrieve fast. We can retrieve fast these words in our trie data structure. So due to this concept of the trie, so what we will do is to create a trie data structure. So this is a rooted tree. Basically we start from the one root, and there is no limitation for the child for this. So this is a normal tree, so tree can contain any number of childs. Okay, so there is no binary or term is used for this. So other than root, each node labeled by a letter from input letters. Okay, so every label, so for example, this is a starting part, this is a root node, and after that every nodes contain a single characters. Okay, so for example, if English characters contain say 26, so this node can contain any character inside it. So every node contains a single character, and children of a node have distinct labels. So so this is a different label. So for example, here we are starting from the root, and the first label will contain is one character, and second label will contain a different type of characters. So this is depends on our storing the words. So for example, here our dictionary is this, so we want to store this all words. So here 1 2 3 4 5 6 7 8. So how we can store this words in our data structure? So when we when the searching is required for any word, so we can search faster of this type of information. So here you can see, so this bear, BEAR, and BELL. So here this BE is common for both. Okay, so there is no need to store every word separately. We can store these word in our trie data structure. We can save space by storing this common suffix uh, at only one time in our trie data structure. Okay, so what is the structure is basically we will start from the root. So root is basically for the practical creation. We can take a dictionary. Okay.
Sir, how will we store bully? BULLY.
Yeah. So for example, if we are creating this trie data structure, so for root, if we are getting this B value first, okay, so we will start, we will store first word in our trie data structure. At that time, we will see what is the first character. Okay, so what is the first character is B. We will make this B as a child of this root node. After that, next character is E. So E is a child, E will be added as a child of B. Okay, so every
No,
time
in this tree, in this set of words, if we add one more word after bull, say bully, BULLY.
okay,
How will that go in this tree?
so BULLY basically we can, okay, so okay, bull is here. So yeah, is there any condition for that? If any word is completed, for example, BULL already is a word. So after, so for identifying this BULL, so is there, where is BUL? Yeah, so this is one BULL. So for identifying, because BULL is also representing one word. So for identifying this, we can add a and characters. So after this, for example, we practically we add one and character in next node. So using this, we can identify this. This is a bull word. If you want to store bully, so after that we can make a second child of this L. Okay, so we will perform the same BULL, and after that we will add one more, and we will add the L, and after that we will store this ending character like dollar. Okay, so uh, after every last character of each word, we will add one extra node which contain the ending signal. So we can take any ending signal which are not which is not the part of our actual characters. So here, if you want to search this boolean, so we will see in our dictionary from the root where is the B. Okay, so we will move to this B. Then when we will check that U part. So if B, we will check this dictionary. So every node is contain a dictionary actually. Okay, every node contain a dictionary. So in dictionary, we will check that is there any child is available which contains the U. Yes, there is one child available U. Then in the next part, we will check the dictionary of U. We will check the child. If any child is contain the value L. Okay, so there is one L. Now same process for the next. we'll check if any child of L is contained the next L character. So yes, this is available. Now same process we will check here. If any child of this L contains the L, sorry, Y, this is we are taking actually bully Y. Okay, so we will check that Y is available as a child of L. Yes, available. After that, we will check the termination symbol is available as a child of this Y or not. Okay, so that means this word this word exists in our data structure. So this termination symbol, this using this termination symbol, we can identify this. This is a actual word or this is a service tag. So for example, if you are searching SEL, okay, SEL, this word is exists in our trie data structure or not. So we will start from the top and we will search that is there any child contains the S character? Yes, it contains. Then we will check the dictionary of S. We will check the is there any child available which contain the E character? Yes, available. After that, we will check the is there any child available which contains the L character of E? So yes, available. After that, we will check is there any child available which contains the termination symbol? But in our L child, if you see this L, so there is no child which contains the end character. That means this is not a word in our trie data structure. Okay. So
Sir,
to
can you
identify
repeat how is storing being done?
storing, okay, I'm creating this new completely one second.
In that case, suppose we have SEL and SELL, both the words in the dictionary, then how will you do that?
SELL. Okay, you are saying okay, one second.
Yeah, both.
One second. So for example, this is a word, and if you do you want to add any other words apart from this?
SEL.
SEL. Okay. So in this process, so BEAR. Okay. So we will start from the root. We will create a one separate root that is the common for all. So after that, we will start storing the word. Okay. So for example, this if we want to store this beer, we will make a child which will contain the B. Okay. After that, what is the next character of this B is E. So we will make E also is a child of this B, and A after that A and R. Okay, like this. After that, this is a last character of this word. We will add one termination sign. Okay, we will start from the same process again for the second word. We will check. We will first check that for the B. If B is available, then we will traverse the same path. If B is not available, if the character is not available, we will create new one. Okay, so here B is available in our as a child of root node. Okay, so we will move to this B. Now E is also available of the child as B. So we will move to this E. Now L. So L is not available as a child of E. So we will create new like this. Okay. Now next the second L. So the next child of L is not available for this L. So we will create new. Now word is complete. Now we will add one more symbol, termination symbol. Okay, like this. Same for the B bit. So we will start from the root and we will check B is available. Yes, available. Then I is not available. We will create new. Okay. D is not available as a child of I. We will create new like this. And after that, we will add one termination. For the bull, so B is available, but U is not available. Okay, so we will create new U, and L is not available, and second L, this is not available. Okay, so after that termination symbol. BU by, So here B is available, U is available. Now Y is not available as the child of U, so we will create new Y, and after that we will add termination. Same SELL. So S is not available as a child of root node, so we will create new S. E. So for example E and L. Okay, and next L. After that we will add one termination symbol. Now for example, if we want to add this next SEL, okay, so SEL, we will traverse S is available, E is available, L is available. Okay, so available. So if this is making a word, so we will, after that we will create a new child which will contain a dollar. Okay, now for the stop, S is available, T is not available as a child of here, so we will create for new T, and after that new O and P. And same for the stop, T is not available, we will create new T, and O, C,
No, T is available.
O, S is one.
Sir, so when we are retrieving cell, suppose, so when we reach the second L and suppose we, go to the stop character, then won't that cause a problem?
No, at the time of searching. So for example, if we are searching SEL, okay, we will check this S as a child of root node is available or not. So S is available, then we will check the E. If E is available as a child of S, yes, available. Now L. So okay, L is also available as a child of E. After time, so our word is completed. Now we will check that. So this dollar sign is available as a child of this L. Okay, so we consider this is our word in our dictionary.
So
This
can we take it like if I am searching for SEL in the entire thing, then actually I am searching for SEL and a terminal character?
Yes. So every time we will after complete the word, we will verify this by termination condition. So this word is a actual word, or this is this is only a suffix.
Exactly. So
We can identify
if I'm
termination.
searching for SEL,
Hmm.
then I am actually searching for SEL and the terminal character. And in the try entire thing, if there is after, I mean, in that branch SELL, if after the first L there is no terminal character branching out, so that means there is no SEL in the
Yes.
dictionary. Otherwise, it is
Yes.
available.
So if CL is not stored at the time of storing, so definitely this is not a word. So during this time, if we are searching this SEL, so we will, after reaching this L position, we will check that its termination symbol is available as a child or not. So this is not available. That means this is a this is a prefix of any word, not a word. Okay.
Got it.
Yeah. So for last word is stock. So S is available, T is available, O is available, and after that we will create a new C and K, and then dollar. Okay. So this is the creation of our trie data structure. So after storing these all characters, you can search any character in total number of length of the characters steps. So for example, if you want to search this bull, so you can search this bull in our data structure only 4 steps. No need to compare all the words in our data structure. So for example, if you are storing these words in a simple list, so at that time you have to compare all the words by our searching word. This will take more time, but here you can search this bull word in our trie data structure in only 4 steps. Okay, so we will use the dictionary things we will use the dictionary for storing each child. So in dictionary we can search any character in order of one operation. So because of that, total 4 operations is required to search bool in our trie data structure. So okay, so this is a creation process. So same process we will apply for the searching. So we will compare the first word as a child of, we will check that if first character is available as a child of root node. If it is available, then we will move to the child node, then we will check the second character. If it is not available, then we can directly return that this word is not available.
So root node will be having as many children as the
Yes.
starting letters of the words in the list.
Yeah. So these
Yeah.
this first label contain the starting of the starting character of the each word. Okay. So this is a process of the trie data structure, or we can implement using this dictionary and simplifier. Implementation, I think sir have given the implementation. Otherwise, the implementation is given in the notes. If you want to see the implementation, so trie data structure. So here you can see the implementation of this. So basically, what we are creating a root node as a dictionary. Okay, so after that, every time when we want to perform add operation, so we will perform this add operation using this. Okay, or we can also create a data structure by giving the initial words, list of words, using this as equal to list. At the time of object creation, we can provide the words list, and so this loop will create a trie data structure. So you can see in the at the time of storing the words, so we are taking this $sign. Okay, so this is the process. So every time we are creating a new dictionary, when we are adding a new word, and we are just we are making a key. Every time we are making a character as a key for the next level. So same process we are actually applying for the searching process. So here this is a searching process. We will start from the root. So we basically initialize with the root. After that, we will check that if C in S. Okay, so we will move to that if C not in the current key, return false. Otherwise, we will move to the current. We will read the node value CURR as a key value of the dictionary. Okay, we will repeat this process, and we will check the next character. So using this for loop, we will check the each character in our dictionary. So after that, after checking all the characters, we will match that if $sign in all the last character keys available or not. Okay, so this dollar is representing the end of the word. So if dollar is available of the last character dictionary, so that means this is a word. Otherwise, we will return the false. So this is a simple implementation of the trie. We can store our words in this format, and we can search in the time which is equal to the length of the searching word. Okay, so is it clear trie data structure, how we can implement this? And so implementation is easy. We are using only dictionary. So some application is given. Apart from that, some application is also given of the trie data structure, how we can use. So we can also store the suffix. So in the next part, I think, so this is the trie data structure. And we can also store this information in for our text. For example, if we want to store a big text in our trie data structure, so we can also store this information where this word is actually appearing in our text. So this is containing a position, index position, where this as this bear word is coming. So this bear word is coming in our text at index 6 and 69. We can also store this information. So using this, we can search our word fast. So you have already seen the pattern matching algorithm. So we have already applied some matching algorithms to finding out the match index. So here you can see we can finding out. So for example, if you want to search BULL in our text, so there is no need to compare from the starts. We can direct, if our these text is storing in our trie data structure, we can directly found this information using the traverse of the child label. So VEAR, after that we can get this information. So BR is available at the 6 index and 69 index, and bool is available at the 30 index. So at the time of storing, we can store this information. So after that, when we want to search any word in our text, so we can return this quickly. So this is the one application. So other things we can also, this is the implementation, suffix trie. Yeah. So suffix trie is also a similar type of thing. So for example, this is our word. This is a word which we want to store in our trie data structure, and we want to store all the suffix in our trie data structure. So after that, we can check that this is a suffix of this string or not. Okay, so from the root, you can see that every suffix. So suffix is, for example, this A. So A is a suffix. So after A, you can see that this is a terminal point. Okay, so this is a terminal point. That means A is a suffix of our string. So BA is also a suffix. So after BA, you can see that there is a termination point. So at the time of creation, we can store this information. After every suffix, we can store this termination symbol. So at any application, so for example, KMP algorithm, where we are using this information, suffix and prefix matching. So we can simply search this information. This is a suffix of our string or not. We can directly search this information in our suffix trie. So this is also a application. We can identify this task quickly using this trie data structure. So this is a building of the suffix process. Yeah, is W a substring of S or not? This is, so here we are identifying this W is a substring of yes or no. So we can also perform this task. So these are some application. Important thing is the trie data structure, how we can create this trie data structure, and how we can perform this searching and storing things efficiently if we are storing a similar type of words. So any query in the trie data structure? Okay, trie data structure. Veena is asking for hello. I just joined. What are we doing? So Veena, if you have any query in week 10 and week 11, so you can ask here. So this is the open session for both weeks. So any content, any topic you want to discuss, you can ask. Okay. So any query in this trie data structure? Okay. And week 11, have you watched all the videos of week 11? Any query? Only first lecture I watched. Okay. Okay, so I'm moving to the week 11 contents. So week 11 is basically 2-3 topics have mainly discussed. So linear programming is the first topic, and second is the maximum flow network, and third is the reductions of the problems and intractability. So first topic is the linear programming. Okay, so what is linear programming? So linear programming is also a way to solve the problems. Here we can model our problem into a linear functions, and after converting this linear functions model, we can solve on this. So you have already seen, so we are solving till now we are solving different types of this optimization problems, where we are finding this type of things, optimal things, shortest, minimum, longest, maximum, this type of things. So this is called the optimization problems. So this type of problems we can also solve using the linear problems. Not all the problems, but some problems we can solve using this linear programming approach. So what is the linear programming approaches? Here, basically, we convert our problem into two objects. First is called the constraints, and second is called the objective. Okay, this is a constraint, and this is an objective. So what is constraint representing here? Constraint representing is that what are the condition we have in the problem. So for example, if we are solving a problem, and what are the condition or what are the constraint given to us for the problem, to solve the problems. So if we can convert this constraint into a linear function. So linear means here we can take any variables, but every variable can be multiplied by any constants, but we cannot multiply by variable to another variables in our equation or functions. Okay, so we can simplify this expression. If you see this expression here, so here x1, x2, this x, and this is a variable of our problems, and here we can simply multiply this variable by a constant, or we can sum this sub part of this function to the other part of the function. So in linear function, we cannot multiply one variable to other variables, or we can also not multiply the same variable to same variable in our equation, like x square, like x cube. This type of things are not a part of the linear functions. So for solving the problem, if we can convert our problem into this constraint things in the linear function, and same for the objective. This is the objective, what we want to get information. So what we want to this optimization things, maximum, minimum, this type of things. If we can also convert this objective in a linear function, so this is called a objective functions. So this will actually, this function will represent the output. So here the max, this function should return the maximum or minimum things like this. But every function should be a linear function. So if we can convert our problem into this model, so we can apply this linear programming concept to solve. So here sir given one example of the suites. So some constraint are given in the problem statement also. So here the one condition is given. So this burfi, so cashew burfi and dry fruits halwa. So any sweet, so this grandiose sweet sales these two types of sweets, and he's getting the profit for each box of Burfi is rupees 100. So this is a first condition. So if they are selling a one box of the Burfis, they are getting the profit of 100 rupees. If they are selling the one box of halwa, they are getting the profit 600 rupees. So this condition is given in the problem statement actually. So we will note down every condition, and after that we will create a linear function on that these conditions or constraints. And this is the first things information is given. Second condition is given. For example, the daily demand for Burfi is at most. Maximum demand for per day of the Burfi is only 200 box. Okay, and daily demand for halwa is at most 300 box. So there is one constraint is given for the daily demand. Okay, so we will note down every type of this information first, and next thing is staff can produce 400 box a day. So this is a limitation. So our the suites of staff can only produce 400 box a day altogether, either of Burfi or either of dry fruits or the combination of both. So after noting down this information, so yeah, these are the points which are representing basically a constraint or conditions. And this is the next point: what is the most profitable mix of Burfis and halwa to produce? So this is basically our objective. Okay, so this first all points are representing a constraints, and this last is representing our objective. So this is the most profitable, that means maximum profit. So what is the combination of Burfi and halwa box to produce, which so we can get this maximum profit. Okay, so after noting down this all points, we can convert this into our linear programming models. Okay, so this is basically a model. So first step is creative variables for this type of model. So we are just assuming that we have B boxes of Burfi to produce per day. Okay, and H number of boxes of halwa to produce per day. So we are taking this two variable which are representing a number of box for each type of sweets. So after finding out this variable information, we will make the linear function. So this is our objective function. Okay, we can say that this is our objective function. So profit, basically we can represent that. So we are getting the 100 rupees profit per box. So if our number of box are B, so total profit of the for the Burfi is 100 into B plus 1600 into H. So this total value is representing a profit, and our main objective is this should be a maximum. So what value we should take for the B and H? So this value is a maximum value. Okay, so this is our objective, to find out the maximum profit. So that means the value of this equation is a maximum. So this is a linear function. You can see that this is a linear function. Next thing, so this is the first objective function. Now we will identify the constraints. So constraint is that daily demand of Burfi is at most 200 boxes. So we can write the first constraint: B cannot be greater than 200. Okay, so this is the first constraint. Same things for the here. H cannot be greater than 300. So we will also represent this equation. And next things, the staff can produce 400 box. So this is the next constraint. Production constraint B plus H is less than 400. Okay, so this is the next constraint. So we are creating this constraint, and this constraint is also a linear functions. So we'll ensure that every function should be a linear function. So after that, there is one implicit constraint. This value cannot be a negative. The value of B and H cannot be a negative. So we are adding this two constraint by default. Okay, so the number of box and the box of barfi and box halwa cannot be a negative. So we are just assuming that b is greater than equal to 0 and h is greater than equal to 0. So this is a linear programming model. So we have convert one scenario of the problems into a linear programming model. So we have created the objective function. We have created the all constraint functions. After that, we can solve this. So there is one approach is given using a graph we can create. So here we can solve this using a pictorial representation. So you can see that after here the one line is representing a number of halwa boxes and this line is representing a number of barfi boxes. Okay, so we can simply draw the lines using these constraints. So first here two values are given, b is greater than equal to 0, h is greater than equal to 0. So that means h value cannot be go down here. Okay, so there is one constraint, that means this line. So value of h cannot be lower than this. Same for the h value cannot be negative. That means h value, b value cannot be negative. So b value cannot be moved this side. Okay, so these are two lines I have created. That means these are the boundary, and we will take this condition. So b is less than equal to 200. So b values cannot be more than 200. So we will also create a one line here. Okay, so our b value cannot be moved, cannot be crossed this 200 value. After h value cannot be greater than 300. So we will perform one line here. Okay, and b plus h should be less than equal to 400. Okay, so this line will be represented like this. So for example, if we are taking this 300 value, okay, for h, so that means 300 plus 100, this point, so total will become 400. And same things here, if we are taking this 200 barfi for 200 box for halwa, and so we have to take this value point here. Okay, so our next line will become by crossing this point using this constraint. Okay, so these are the region where our we can get our answer. Okay, so this is called a feasible region where our solution will exist. So we can solve. So there is one way to solve this. We can apply the every single value for b and h and get the maximum answer for this equation. Okay, for every combination. But if we are getting this type of feasible region, so this is also called a convex region. So convex region means if we are getting this something is called polynomial convex type things. So this convex means if we take any two points in this region and we create a line, so that line should become under this region. That is called the convex region. Okay, if for example our polynomial image is like this. Okay, here we are taking these 2 points inside this region, and we are making a line. So this line is going outside of this region. So this is not a convex region. So if we are getting this convex region, we can get our answer by taking these crossing points. So we can simply check our solution for these points. Okay, these 5 points. So we can take 0, 0 value definitely for 0, 0. There is no, this is not possible for the maximum profit. We can take 200 and 0. We can take 300 and 0 combination. So here we can take 300. So h value equal to 300, and b value we can take 100. So total is 400, and we can solve it. We can put this value inside this expression. Okay, so 100 into b, so this is 100 plus 600 into 300. Okay, what value we are coming to 10,000. and this is a 18 4 times 0 plus 10. This become 190,000. Okay, so for this point we are getting this 1,90,000, and we will also check for this point. So this point is 200 and 200 for both. So 100 into 200 plus 600 into 200. Okay, so this is a, so 20,000 plus this is 12. Okay, this become 1,40,000. Okay, so we will calculate the value for each point. So generally we can see that we will consider as a vertex, and for each vertex we will compute this objective value, and we can check that for which vertex we are getting the maximum value. That is a solution for this problems. So if we are taking this value, so for this point, okay, for this point, if we are taking the H halva box equal to 300 and Burfi box equal to 100 box, then for this value we are getting the maximum profit. Maximize these things. Okay, so we can use this linear programming model to solve many type of this optimization problems. Okay, so this is also a good approach to solve many problems. Is it clear?
Yes, sir.
Okay. So yes, sir, have given the different types of example for this also. So not every problem can be modeled. So sometimes if we want to model any problem to a linear programming model, so we have to take many numbers of variables, so that will become complex. So there is one different types of method to solve problem is maximum flow. So in lecture 2, actually, sir, lecture 2 and lecture 3, sir is giving some different type of scenario where we can use this linear programming models, and sometimes this linear programming models get complex. So we can use the alternative approach. That approach is called the maximum flow. So I'm moving to this maximum flow topics. This column. So here one network is given. So for example, this is a oil network. Okay, so network of pipelines. So these all edges are representing a pipeline, and every pipeline is representing a capacity of the flow. Okay, so this is a source. S is representing a source, and T is representing we can say the destination. Okay, here the flow is moving to the side of T. Okay, so this is actually producing a flow, and this is getting the flow. Okay, so here so this network is representing an oil network, and every edge is representing a pipe. So, and this value is representing a capacity of the flow of each pipe which are connecting. So for example, this edge is connecting S to A. So this 3 value is representing a capacity of from S to A at any time. So only 3, for example, this is a value given in a liter. So 3 liter petrol can be flow from S to A at any time. Okay, so every edge is representing a capacity on that edge. So direction is also given. So here the 2 values representing it. So the maximum 2 unit can be flow from A to D on this edge. Okay, we cannot flow the greater capacity on this edge, which is greater than 2. Okay, same things for the every edge. So what is the maximum flow of complete networks? Okay, so what the maximum oil capacity can be flow on the complete networks. So this is the question. So this is in the previous lecture 3, actually sir give one example of the net bandwidth allocation in the networks. So how we can decide how we can flow the maximum bandwidth to the users. So same problems here, the scenario is different, but we can solve using this maximum flow network concept. Okay. So, or there is one also constraint. So for example, if for example this B, at this B node, so we are getting this 3 unit input at B. Okay, so from B output should also be a 3. So capacity can be more. So here the capacity is 10, capacity is 1. If we are receiving 3 unit of oil, so definitely output should also be a maximum 3. So input value and output value should be similar during the flow. Okay, so here, so this is actually this value is representing a maximum capacity, but during the flow the value can be less. Okay, so for example, if we are talking about this D point, so here we are getting this 2 value, 1 value, and okay, 2 and 1 value. So that means the maximum we are receiving 3 unit. So we can flow for the 3 also, 2 from here and 1 also. Yeah, so 3. So what unit we are receiving at any point, so we can move further. So these are some constraints and these are the scenario. Each edge is representing a capacity of the line. So network of pipelines ship as much oil as possible from S to T. Okay, so what is the maximum flow from S to T we can get in this network? This is the objective. No storage along the way. So there is no, so that means this node cannot be stored any oil at this point. If they are receiving at any unit, they have to move further, but they cannot store at one. Okay, so this is the next condition: no storage along the way. We cannot store the oil at any point. A flow of 7 is possible. So this is the different things. Is this the maximum? Okay, so this is the different question, but how we can identify the flow? So I'm taking this graph and I will explain the algorithms how we can solve this problem. This is different. Okay, so this is a problem actually, or there is one algorithm, Fulkerson algorithm. So using this algorithm we can solve this problem. So this is the different things. So network special node S called source and same. Okay, each edge E has capacity CE at each node. Yeah, so this is also a condition. Each edge E has capacity CE. So that means this value is representing a capacity. Flow FE for each edge E. Okay, so we are considering that this flow FE on each edge E. So FE capacity C. Yeah. So flow, yeah, that means flow. So this is a capacity actually, and flow can be different. Okay, flow can be different. If you can see that at the node B, so we are receiving only 3 unit here. Okay, so we cannot send the 10 unit on this set. This is representing a capacity, but our flow can be different. So but flow, so this flow, this is capacity, and each edge our flow will always be less than our capacity. So we cannot move move flow greater than our capacity. So this is the next condition. At each node except S and T, sum of incoming flow should be equal to the sum of outgoing flow. So this is also a condition. So if at any node, if we are receiving 4, for example, if at this node C, if we are receiving 4 units, so output should also be a 4. So total volume of flow is sum of outgoing flow from S. So now this is the formulation. After that, we will apply the Ford-Fulkerson algorithm, and we will. So yeah, this is the one, Ford-Fulkerson algorithm, and I'll tell you the process to solve using the Ford-Fulkerson algorithm. Yeah. So we will create a list. So according to the Ford-Fulkerson algorithm, we will select any path from the source to T, S to T. We will select any path. Okay, we can select any path from S to T. So for example, initially we are selecting this S. I am writing this path here: S, A, D, and T. Okay, so we can select any path from S to T. So after selecting the path, so we will check that what is the lowest value on this path. What is the lowest capacity on this path is, which is 2. Okay, so 3, 2, 2. This is representing a capacity of each line. But what is the lowest value of each? This path is 2. That means the maximum flow we can transfer on this path is 2. Okay, so after, so that means we will write these things 2 here. This is the maximum possible flow on this path 2. But after taking this 2, we will reduce the capacity from each edge. Okay, so if we are selecting this 2, we will mark the residual capacity. So that is called the residual capacity after reducing this reducing this flow value. So for this path, we can say that this is a maximum flow, and after selecting this maximum flow, we will reduce the capacity on this edge. So the capacity of this after selecting this maximum flow 2 value, so the capacity will remain 0 at this edge. Same things we will perform on this edge. So 2 minus 2 is 0. Same from 3. Now 3 minus 2 is 1. That means if we are transferring the 2 unit of oils on this path, after that the remaining capacity on D to T will become 0, and A to D will become 0, and the S to A will become 1 remaining capacity. Okay, so we will note down these things. So after selecting this path, we are getting this maximum flow value 2, and so we are getting this remaining capacity. Now this one. Okay, now we will select the second different path. Okay, now you can see that there is no capacities remaining on path D to T. Okay, that means we cannot take the path that is coming from this D to T. We cannot select this D to T path, D to T edge in our path, because there is no capacities remaining on that path. But we can move from S to T via this E edge. Okay, that also containing this 5 things. Okay, so we cannot consider the edge which contains the 0 capacity now. Okay, so those edge containing the value greater than 0, we can select only those edges. So for example, if we are selecting the second path like this SCET, okay, now SCET, so the smallest value on this path is 4. So we will write these things 4. Okay, now after taking this 4 value, what will be the remaining capacity is 0. Here this is 1, here this is 1. Okay, so this is now the second selection. Now we can is there any way we can reach from S to T is available or not? So for example, now it is 1, it is also 1. Yeah, so we cannot select this S to C now, but we can select the path like this S, B, D, E, T. Okay. S, B, D, S, B, D, E, and T. Okay. So all S contains any sub value, and there is a S direction is also moving to this. Correct. So S to B, B to D, or D to E, and E to T. So you can select on different paths also. For like example, so S to B, B to D, and D to C, C to E, and then E to T. You can select any path. So for example, I'm selecting this path. So in this path, what is the minimum value of any edge is 1. Okay. So this is the 1 value. So we can write this thing 1 here. And after taking this 1 value, so this will become 0. This will become 0. And this will become 0. And this will become 2. Okay. So now after selecting these 3 paths, so we are getting these flow. Now you can see there is no path is available after that selection of these 3 paths. So there is no path available where we can reach from S to T, because D to T is now containing a remaining capacity 0. Same for E to T is containing a remaining capacity 0. That means these two edges are available to come at node T, and both contains the value 0. That means there is no flow can not come on now T. Okay, so this is the last step. So at any time when we are not reaching from S to T with any capacity, so that means this is a last step. So now we have completed this process. Now we will add this flow 2 plus 4 plus 1, that is 7. So this is a maximum. This is representing a maximum flow on the network 7. Okay. So this is a process to perform the to finding out this maximum flow value using the fourth Fulkerson algorithm. Any query in this topic? Maximum flow network.
No, sir.
Okay. Okay, so we can solve this type of problem where we want to select, we want to find out this maximum things, maximum flow things, or maximum bandwidth things. So this type of, so many different types of problem can be solved using these models, maximum network flow models. So there are a big category of problem that can be solved using a linear programming, and there's also a big category of problems that can be solved using this maximum flow networks. There is one more topic in this maximum flow network is minimum cut. So sometimes for proving this, what is the minimum cut value in this flow network? Okay, so I'm taking this diagram. So sometimes this is also asked, what is the minimum cut edge? What edge is representing a minimum cut? So minimum cut is actually representing, so what edge we can remove. So after that, there is no path available from S to T. That means there is no connection will remain available from S to T. And there, so these removing edge should store the minimum value. Sum of the sum of the capacity of all the removing edge should be the smaller minimum. So what edge we can remove from this network? So our basically this S we cannot reach from S to T. Okay.
DT.
D to DT. This
Yes,
one.
yes, yes.
But still we can reach from this here S C E T. So if you are removing this DT, only DT, so that means the path is also available. So you can move from this S, B, D, E, T.
Is it allowed to remove another edges or
Yes.
only?
So actually we need to remove the any number of S. So, but the total sum of the capacity of all S should be minimum. After removing these S, our path, there's no path should be available from S to P. But that the total sum of capacity should be minimum. So these things we can identify after calculating this maximum flow. Okay. So after getting this maximum flow value, so 7, we are getting this maximum flow 7 value. So we can remove number of S that where the total sum of the sum is equal to the 7. We cannot remove the S which are containing the greater value of this 7. Okay. So here you can remove like this 2 and 5. So here the value of this capacity is 2 plus 5 is 7. And after removing this S, there is no path available from S to T. Okay. So same things. So there are more than one minimum cut set are possible in our network. So these are the one possible way. Apart from that, we can also remove another. If possible, I'll check it. 5. Okay. So for example, if you are removing this CE, DE, and DT, so we are getting the 5. Wait, this is not a equal to our maximum flow. That means this is not a minimum cut. So we can remove any number of edge, but the value of the total capacity should be a minimum. So we can confirm this minimum value by this maximum flow value. Okay, this 7. So if any question, if we are asking the minimum, find out the sets, find out the minimum cut set of the edge. So this the value you can confirm by this maximum flow value. So another, I think it is not possible. Another set is, I think it is not possible. So 1, 2. Yeah. So I think only one set is available, DT and ET. So if we are removing these two S from our network, so this is called a minimum cut set. So after removing these two S, we cannot reach from S to T, and the value of these two edges 2 plus 5 is 7, and this is a minimum. Or this so this minimum cut value should also equal to this maximum flow. So you can solve this problem also using this maximum flow value. After that, you can simply see the edge where you are getting the sum of edge is equal to the maximum flow, and after removing that, there is no path is available from S to T. Okay, so this is also one important problem, maximum flow network. Is it clear how we can solve, how we can get this maximum flow and minimum cut set?
Yeah, yes, it's clear. There is no code for this, no?
Yeah, so in B12 we are not using any code. Okay. Yeah, so this is the problem actually. After that, reduction. Yeah. So we have already seen two types of method to solve these problems. This is basically, we can say that this is the hard problems. We cannot solve easily, or we cannot solve in the polynomial times this problem. So these are the two ways to solve this type of problems. Next step is reduction. So what is the reduction is basically, so how we can convert a one type of problem into a second type of problems, different type of problems, and then after we can solve this. So there is one example is given by parietic. So what is called biparated? Yeah, biparated matching. So here one scenario is given. So for example, this name is representing a instructor, okay, and this second value is representing a subjects, and we want to assign each instructor as a each instructor to only one subject. But here the instant interest is given. So for example, here the Priya, you can see the Priya can teach biology as well as the maths. Okay, here they can also teach the English as well as the history. So any teacher can teach more than one subject. Okay, and any two subject can be teach by any two instructor also. So for example, if you see this math, so this math is can be teach by this Priya and Kumar also. Okay, so this is the scenario is given, but we want to assign only one subject to one teacher. So how we can solve this task? So this is a simple example, but what happen if this become a big type of problems? So how we can find the solution for this? So this is a one category of the problems by parietic matching. So how we can convert this problem into a another problems like a maximum flow networks? Okay, so we can convert this problem into a maximum flow network like this. So if you can see, yeah, here. So we can create a one extra node before this these name. Okay, this is called S, and after the subject, this is called a T. Okay, this is representing a source, and this is representing a end node T. So sync. This is called representing sync. So we will simply connect every instructor name by this S. Okay, so we are connecting every instructor name by one H S. So S to Sheila, Ajiz, Priya, Kumar, and here. Okay, and so this part is become like this, and same things for the subjects. So here we are adding every subject by a T by one H. After adding these things, we will assign the one value at each edge as a capacity. Okay, we will simply assign one value at each edge as a capacity value, like this. Then we will apply this Ford-Fulkerson algorithm on this problem. We will simply apply. So now this problem become a maximum flow network, and we can solve this using a Ford-Fulkerson algorithm, and we can find out the edge. So for example, if we are receiving this one value at Sheila from S, so definitely from Sheila there is only one capacity can be go outside. Okay, so for example, this Priya, so there are two H is going to the outside. Okay, so Priya to biology and Priya to maths. But if we are receiving one value as an incoming value, so only one H can be so flow can be move only one H with the value 1. So definitely the another edge will not consider for the flow. Okay, so in that case, if we are assigning each edge as a one capacity, so definitely in this part, in this lower part, so only one edge will be connected from this first part and second part with the capacity 1. And for maximum flow, so definitely if we are receiving 5 unit from here, so we will get this 5 value here also. So definitely this 5 value we will get this below network, this network part. So only 5 edge will be selected from the between. So that means every instructor will be assigned as a one subject, assigned by a one subject. So we can solve this bipartite matching problems using this maximum flow networks. So this is called a reduction process. So we can convert. So this is the reduction things. So we want to solve problem A. So here the problem is A. So in that case, this bipartite matching is called a problem A. So we don't have any solution for A, but we can reduce this A problem into a B problems. So you have already seen that we have converted this bipartite matching to a maximum flow network. So we want to solve the problem A, but we have no solution. Now we know how to solve problem B. Okay, we know that how to solve this maximum flow network. So how we can convert our problem A to B? How we can reduce our problem A to B? Okay, so we can reduce our problem A to B. Okay, if we are able to solve this problem A, we solve the problem B, so we can also solve this problem A also. Okay, but we have to apply some pre-process and post-process things to solve this. So here you can see in the bipartite matching. So we have to add this source node. We have to add this edge from source node to every instructor. We have to add this T node, and we have to add this edge from subject to T, and we have to assign the one value on each node as a capacity. So this is called the pre-process things. Okay, so when we are reducing a problem A to B, so same things, we have to perform this pre-process part. Okay, so after getting the result, we have to apply some post-process also to getting the correct answer. So after finding this maximum flow network, we have to identify the edge which are connecting to this instructor to the subject. So that process we have to perform. So this is called the post process. Okay, so basically we want to solve this problem A. After reduction, we have to convert this problem A to a algorithm. We will convert this problem A to B using this pre-process and post-process adding by adding this pre-process and post-process things. And if we are able to solve this problem B using some algorithms or using some process, so we can say that we can also solve this problem A. Okay, so that process is called the reduction. So here for the reduction things, about this, if we want to solve this problem A, and we are reducing this problem A to B. So this B problem, if we know the solution of the B. So this pre-process and post-process, this part should also be solved by some efficient algorithms. Okay, so otherwise, if this is a so for example, if we can solve this algorithm by B, and we know the solution of the algorithm for B, but our pre-processing and post-processing is a difficult task, and this cannot be solved. So that we can see that we cannot solve the problem A using this B. So this pre-process and post-process operations should also be performed efficiently. Then we can see that this is a reduction. Okay, so this is the reduction things. We can convert one type of problem into another type of problems, and then we can solve. So same things in the reduction topic. So bipartite matching reduced to a maximum flow, and maximum flow can also reduce to a linear programming. So in the second lecture, actually, not the second, in the third lecture, actually, sir explained the bandwidth allocation of the network. In that case, sir explained how we can represent this network allocation or this flow things. We can represent into a linear programming model, but this linear programming model is becoming more complex. So because of that, we are not solving this using a linear programming. We can solve using this maximum flow, but the problem can be converted into this linear programming model. So that means, so any bipartite matching problem can be reduced into a maximum flow, and any maximum flow can be reduced to a linear programming. So using this number of variable constant in the linear of the size is linear in the size of the graph. So these type of things we can reduce one problem to another problem. So reverse interpretation is also useful. Yeah. So reverse interpretation is, yeah, this is a point. If we are say after reduction, if we are saying that if A is known to be intractable and A reduced to B, then B must also be intractable. So here intractable, what is the meaning of this intractable is? So intractable means any problem that cannot be solved in the polynomial times. That can be solved in exponential times, but cannot be solved in the polynomial time. And those problems can be solved in the polynomial time. That is called the tractable problems. And those problems cannot be solved in a polynomial time. That is called the intractable problem. Okay, we will discuss these things in the coming slides. So you should know what is the intractable and what is the tractable meaning here. Okay, so if A is known to be intractable, that means this problem cannot be solved in a polynomial times, and A reduced to B, and we are reducing this A reduced to B, then we can say that B must also be intractable. Okay, so that means B must also be intractable. That means B cannot be solved. We cannot solve in the polynomial term. Okay. Otherwise, if we are saying that if A is known to be intractable and B is tractable, that means we can solve the problem B in the polynomial times. So using this B algorithm, we can also say this A is also a tractable problem. If we are solving A using this algorithm B, and if our B is a tractable problem, that means we can solve this B using in the polynomial time. So we can also say that these things A can also be solved in the polynomial times. So this is the interpretation. So if A is known as the intractable problem and we are reducing A reduced to B, then B must also be intractable. So this apply from the both sides. Yeah. So in the next point, it is given that otherwise efficient solution for B. So here efficient meaning this if B contain any efficient solution in the polynomial time, then we can also say that A is also contained the efficient solution. That means A is also containing polynomial solution. Okay, but here we are actually more focusing on the this intractable problems. So this polynomial things you have already seen in the seen till now in the week before week 10. So every problem, so complexity, if you are getting this type of complexity like n square and log n, so that algorithm is called the polynomial algorithm. So if any complexity if you are getting like this exponential like things, so 2 to the power k, 3 to the power k, like this thing, it's called the exponential. So here actually we are discussing this type of problems. So big hammers have been added about power tools. Yeah. So these two topics is actually powerful tools to solve this non-polynomial types of problems. Okay. So we can solve this many type of problems using these two models: linear programming and network. So these are the two powerful tools to solve any problems. Many algorithm problems can be reduced to them. Yeah, so we can reduce many problems into this either in linear programming or in the network flow. After that, we can solve. So efficient of the self implementation are variable useful to understand what can and cannot models in terms of LP flow. So these are the things. So yeah, so these are two important things: linear programming and maximum flow. So we can reduce many problems into these two types of models. After that, we can solve. Okay. So because of that, these two types of problem we have discussed. So this is a reduction things. Any query in this reduction? Okay. Okay, so next is intractability checking. Yeah, so intractability checking algorithms, basically what is the checking algorithms? So checking algorithm is one of such efficient solution. Unfortunately not. Yeah. So this is the concept of checking algorithm. So where there are two processes actually. One is the generating versus checking. So what is generating? So generating is the things when so for example here one scenario is given. So for example, one teacher gives some assignment to the students, and so here the one problem is given. Given n number n is given, find p comma q such that pq into pq is equal to n. So factorize a large number that is the product of two numbers, two primes. Okay. Given n, find pq such that pq equal to n. Yeah, so one n number is given, find out the two prime numbers where the multiplication of this prime number is equal to n. So this is a problem. Actually, this is given by the teacher to the students. So the solution, so for solution for this problem may be a difficult and cannot be solved in the polynomial time. So that things, this is a, so solve this problem is called a generating process. Okay, solving a problem, we are called that this is a generating things. So after, for example, after solving the problem, students submit the assignments. So after submit the assignment, teacher want to validate the solution. Okay, teacher want to validate the solution. So teacher can easily validate the solution using this formula. He can directly multiply these two prime numbers and he can compare the solution. If here if p into q is equal to n, so that means solution is correct. Okay, so teacher can simply validate this solution using this formula p into q equal to n. But here you can see the solution is difficult, but validating, or we can say that checking is easy. Okay, that means our solution is a taking exponential time. Here we are actually checking all the numbers. We are checking all the numbers, and after in the factor number, and we are checking that number is prime. After that, we will multiply all the prime, and then we will check that we are getting the number n equal to or not. So it will take some time, and this is the, I think, solution is a exponential solution for this to solve this problem. But teacher can validate is in a polynomial time or using this equation like this, p into q equal to n. So for example, students are returning this p value and q value. So teacher can simply validate after multiplying this p into q equal to n, and then he can say that the answer is correct. Okay, so there are two types of things, generating and checking. So for example, if our generating process taking a time, taking in non-polynomial time, and our checking process is efficient, and it is done in a polynomial time. Okay, so this things actually is called the NP NP problem. So I think NP something. So yeah, this thing is giving checking algorithm. So this process of checking algorithms. Here we can also say that this is a validating algorithms. Okay, so checking algorithm C for problem P takes an input instance I. So it will take the input instance I for problem P, and its solutions. It will give return the solution certificate S for I. It is correct or not? It is true or not? Valid or not? Okay, C output yes if S represent a valid solution, no otherwise. So this checking process, if we are performing efficiently or in polynomial time, so we can see that this type of problem is called the NP problems. So I think NP here is not okay. Okay, so this NP things is discussed in the next lecture. So the definition is the same. If our generation process is taking non-polynomial time and our checking process is taking polynomial time, then that type of problem is called the NP problem, non-deterministic polynomial problems. Okay, we will discuss it later. So yeah, so this is a concept of checking algorithms, and what is the generation, what is the generating, and what is the checking things. So checking is basically to validate the solution, if answer is correct or not. So you, for checking the solution or checking the algorithm, we use this Boolean satisfiability process. So Boolean satisfiability. So in this process, we can decide any variables for the problems. So like here x1, x2, x3, this is the variable we can define for the checking process. And so you know that these are the Boolean operators are given. So we can use this negation operator. So if we are taking the x value true, so this operator will convert it into a false like this. We can use this or operator, and we can use this AND operator. So here these x1, x2, x3, this is actually Boolean value that will contain a true or false value, and we can use these operators on the Boolean value. So for checking process, actually we will create some clause. So so we will create some clause for checking the problem. So for here, for example, here formula C. So C of the form. So we will create a clause like this. So we will create a clause using literals, that is called the Boolean value x1, x2, x3, xn, and we will use these operators or and or negation. So using these literals and operators, we can create a clause to check the solution. Okay, so after creating this clause, we will collect the solution, and we will check the solution according to this Boolean things. Simply we can so for example, we are simply creating a condition for the solution. If this condition is true, we are assigning the true value. If this condition is a false for the solution, and then we will assign the false value. So we will just create this type of condition variables, so Boolean variables, and we will assign some value according to the solution we have received. Okay, so after us getting this value for x1, x2, x3, after getting this value of x1, x2, x3, we will apply this value in our clause, and we will check that if our clause is returning a true value, then we can see that the solution is correct. If our clause is returning a false value, then we can see that our solution is not correct. So we can create this type of clause for checking our solution. So this is the different types of things. Formula conjunction of clause. So there are two types of clause we can create. So this is a disjunction basically. So in every between every variables, we are using this OR operator. So this type of clause is called disjunction of literals. Okay, and if we are using AND operator, that means this is called a conjunction. Okay, so this is C1 is actually representing a one clause, and this is representing second clause like this. So we can say that this is a conjunction of clause. So Boolean satisfiability, assigns suitable value true and false to every variable, so that the formula evaluate to true. Okay, so we will receive the value for each variable from the solution, and then we will check that our clause is true or not according to this input value. If we are getting the true value, that means our clause is true, and then we can see that solution is correct. And if we are getting false value, we can see that solution is incorrect. So after creating this Boolean clause, we can check the solution things. So here you can see that for this clause, if we are if we are taking this x1, x2, and x3, x1 true, x2 true, x3 false, then this clause will be written as a true. So we can say that our clause is returning it true. That means solution is correct. So otherwise, if we are taking x1 equal to false and other things, then definitely this clause will return for false value. So we can design this clause for checking purpose for any problems, and we will simply check our solution is correct or not using this clause. So that process is called the Boolean satisfiability problem, and so this is a different type. So okay, so this is the one example is given where the condition is false. Now there is no satisfying assignment. So here this process is given generating a solution. After the generating a solution, try each possible assignment v2. So each possible assignment v2, we will assign these variables x1, x2, xn. After that, so for these values, so for example, for every variable we can take two value, true or false. Okay, so these are the 2 to the power n possible assignments are there. So these are the all possibility for the value x1, x2, x3. So if we have an n variable, then that means 2 to the power n possibilities there, but no need to check all. So is there a better algorithm? Not known. Yeah. So yeah. So yeah, here this is given. Is there a better algorithm? So for this type of checking problem, so we have to check for all possibility. Okay. So there is no better solution is available for that, for this type of problem. Checking, yeah, checking a solution given formula f and valuation bx for each x, substitute into formula and evaluate. So we will just give this value of x variables into our formula, or we can see that the clause, and then we can validate things. So here one format is given. So actually, if we are taking this type of conjunction, so there is no limitation of the conjunction. So x1 and x2 and this type of conjunction. So this is called a set. Okay, so satisfiability. So here we can take any number of variables in a one clause, and different second type of formulation we can create using this disjunction of clause. Okay, we can create a one clause, and then we can take or operator, and then we can take second clause and we can use the or operator. So in or operator, for example, if we are taking the clause by combining this or operator, that means we are using this disjunction of clause. So for example, C1 is true, then we can directly return true answer. Okay, if any value of the or operator is become true, then we can directly return true. There is no need to check the remaining part. In the or operator, if we are using or operator, so we can return if any value is true. That means the overall answer is true. So we can formulate this type of clause for checking purpose. So we can just create a clause one, C1, then or operator like these things. So it will reduce the time for checking. So each clause force to a unique valuation, try each clause is sequence. So yeah, here one example is given for the traveling salesman problem. So these some problem is given, so that is difficult to solve, but easy to validate. So some if some value is given for validating, if any value is given, so like this for traveling salesman problem. So what is the minimum cost cycle? So simple cycle x y z to x of minimum cost visiting all the vertex. So basically in traveling salesman, we find out the cycles that visit that contain all the vertex, and that is a cycle. Okay. So solution is very difficult to find out this type of solution, but validating, we can simply validate that by calculating cycles. We can check that this is a cycle and this contains a smallest value. So designing a checking algorithm must give a yes and no answer, and given a graph G and a proposed solution as, we can verify the S is a cycle. So this is only a validation part. Simply check that this is a cycle or not, and compute its cost, and how to check that S is the least cost of cycle. So transform the problem. Okay. Is there a tool with cost at most K? Okay. So actually this part is difficult. If this type of value is given, for example, for validating things, if this value is given, if cost at most, is there a tool with cost at most K? This type of things we can easily validate. Here, if we will directly check that if our tool is a cycle and the cost is at most K or not. So now given a solution S, we can check it directly. So, but finding out that so each cycle in our graph, this is a exponential things. So for the original problem, cost is the at most sum of all edge weights in the graph. So this traveling salesman problem, I refer this as a solution to the cost. Transform the problem, is there a tool with cost at most K? Solution as we can check it. Yeah. So actually these two types of two different types of scenarios given. Basically for this one, this part is difficult to check, but this type of information we can easily check. So for transform the problem, we can transform the problem into this type of category. We can simply check this type of information. Is there a tool with cost at most K? Okay. So at most K things, we can simply check this is a cycle or not, and then we will just compare the total cost by comparing this value. If the total cost is at most is representing this K, so we can return a solution. So for the original problem, cost is at most the sum of all the edge bit in the graph. So we can simply validate this problem by comparing this K value. So find optimum K, test different value using binary search. This type of these things is not clear. Okay, currently I'm not getting this traveling sales 1 point. Oh, I'll tell you this later. But the next example is given as an independent set. So independent set is also things U and V are the independent if there is no edge. So what is the independent set in our graph is? So maximum number of vertex that maximum number of vertex that is not connected by any edge. Okay, that is called the independent set. So if you see that this 3, 4, and 5, these all 3, 4, 5 are not connected by any direct edge, and these are the maximum number of counts. So the answer can be different sets, but the maximum value is a 3. That means the answer is 3. Total 3 independent sets are there. We can also select the different answer like this one. So 3, 4, 5. There is one possibility. We can also take this 1, 4, and 5. Okay, this is also a one possibility. That is called the independent set. And the condition is given. Use an independent sets of each pair. So these are some problem actually given using in this category NP problems. So the finding this independent set is a difficult task, but we can validate by the number of maximum things. So we can simply, for example, someone is returning an answer. 3 sets are available, 3 vertex are available as independent set. We can simply validate by this number value 3. Okay, but the finding the solution is difficult. And this is the exponential time. So this is also coming in the NP problems. So similar independent set, there's the next problem is vertex cover. So here some example is given for this things. So vertex cover things. So node U covers every S U comma V incident on U. So number of so vertex cover. So where we can, so this is the minimum things. So minimum number of nodes if we are selecting. So all vertex should be covered. Well, all edge should be covered. So for example, if we are selecting this 2, okay. So that means from 2 total 4 edges covered. Those edges are connecting on this 2. We will mark on that. Okay. So after that we can select, for example, this 3. So we are selecting this 3. These all 3 edges are covered. And after that, if we are selecting this 7, so that means this 6, 4, and 5 is covered. So now after selecting this 2, 3, and 7, so that means all vertex, all edges are covered. So this is the solution. So 3, we can say that. So this is the minimum number of nodes. So there is no possibility to select 2 nodes, and after selecting of these 2, we can cover all the edge. Okay, so there is no possibility. So this is the answer for this vertex cover. So this is another example. And vertex cover information we can also get from the independent set information. So some problems can be like this. So for example, if we want to set the camera for surveillance, so on the roads, so minimum number of cameras. So how many number of minimum camera is required to set up on the roads? So this type of problem can be solved using this vertex cover problem. And there is one formula is given. Yeah, so if you can calculate this independent set of size k, then you can directly return the vertex cover of size n minus k. Okay. So for example, so here if you can see that the total number of independent set is this 3. Okay, so n is equal to 1, 2, 3, 4, 5, 6, 7. So n equal to 7, and the answer is 7 minus 4 is 3. The answer is 3. Use an independent set of size k. Okay, if V So let's view. You see vertex cover. No, that is it's not clear. Connecting image of vertex. Okay. Okay, so this I think next one lecture is remaining and key things. So we will take one extra session in this week, either on Saturday or Sunday. So these last things of last 2 lectures we will discuss on this. So till now, if you have any doubt, then you can ask in week 10 or week 11. So there is one session on the Fridays, week 10 live coding. So we will conduct one more extra session either on Saturday or Sunday. So in that we will discuss this latest weeks, 11 weeks, last 2 week topics. Apparently some things I am missing. So if you have any topic before that, these topics, you can ask. Yeah, Bimlesh, Lakshminandan, Sanjeev, Bina, Yusuf. Any query? Okay. Okay, so some topics are remaining from the week 11. So last 2 lectures. So we will discuss in the next session. If you have any query before that, you can ask. You have to study week 10 and week 11. Oh. So I think 17 is the last date to submit the assignment for week 10 and 11. So you should, I think, watch. Okay. Okay, so we will inform you the next schedule of the session for this week 11. And otherwise, we live coding is on Friday. Yeah, Bimlesh, how was your quiz? Bimlesh, others. Quiz 2, what is the feedback for quiz 2? Difficulty level?
It's not easy.
You are not audible. Your voice is very low.
For me, it is little difficult.
Difficult?
Yes.
Oh, okay. Okay. And Bimlesh? Okay. Okay. Now I'm closing the session. We will meet in the next session. Thank you all.